So continuing with our previous one, we will see about convergence criteria. So the convergence of the finite element solution can be achieved in the following three conditions that are fulfilled by the assumed displacement function. That is, a displacement function must be continuous within the elements. It should be continuous. This can be ensured by choosing a suitable polynomial function. So as we discussed, choosing a polynomial, appropriate polynomial function is one of the important steps in this finite element method, because if we won't choose a appropriate polynomial function, it leads to the errors in the errors. So choosing a suitable polynomial function is very important. So for example, for n degrees of polynomial, displacement function in one-dimensional problem can be chosen as u is equal to a naught plus a1x plus a2x plus a3x plus a to the power of x to the power of 4 plus up to a to the power of x to the power of n. So then the second point is the displacement function must be capable of rigid body displacements of the element. So the constant terms used in the polynomial should be a naught to the power of a to the a to ensure this condition. And the next part is the displacement function must also include the constant strain states of the elements. So as the element becomes infinitely smaller, strain should be constant in all the elements. So hence the displacement function should include terms of representing constant strain rates. So these are the three main conditions for the convergence criteria. So next is model interpolation models. So the basic idea of this finite element method is the piecewise approximation. So as we discussed, so we divide into different number of parts called as elements. So that is the solution of the given problem is obtained by discretizing the given body or a continuum into a smaller number of parts. So these parts are called as elements. So this we have discussed. So and what we do is we assume for a trial function for each and every element. So the assumed trial function we assume because the displacement variation for the elements are unknown. So the displacement functions are unknown. So in order to make this, what we do is we assume a known trial function. So these functions are called as interpolation functions or approximatic functions or interpolation models or displacement functions or displacement model. So these trial functions are known by many of these terms. That is, interpolation terms, interpolation polynomial, interpolation for approximating functions, or interpolation model or displacement functions. Okay. So what are the different types of interpolation models or interpolation polynomials that we choose over the functions? So generally there are two types of displacement models which are assumed to approximate the solution over each element. One is a trigonometric function and the other one is polynomial function. So these are the two types of displacement models that we assume for a trial function or displacement function or displacement polynomial. So over the trigonometric function, these polynomial functions are used widely because of its easy way of solving the problem in comparison with this trigonometric function, and its easiness for deriving the equations or the solutions. Okay, and it can be formed easily. So out of these two types of interpolation models, the polynomial interpolation model is the most widely used to the following. What are the as it is easier to perform mathematical calculations such as differentiation or integration. So in comparison to trigonometric function, there is a polynomial function that is easier to perform the mathematical calculations such as differentiation or integration. It is easy to formulate and computerize. It's easy to formulate and computerize. And one more thing is it is possible to increase or decrease the accuracy. So it is possible to increase or improve the accuracy of the results by increasing the order of the polynomial. And next is the polynomial form of an interpolation model. Polynomial form of an interpolation model. So the general of the polynomial displacement function or the one-dimensional case is given by phi of x is equal to alpha 1 plus alpha 2 x plus alpha 2 x plus alpha the power of n next to the power of n. Or else we can give a1 plus a2 x plus a3 x plus up to an next to the power of n. So similarly in 2 and 3-dimensional finite element, the polynomial form of an interpolation function can be expressed in the form as phi of x comma y equal to a1 plus a2 x plus a3y plus a4 x plus a5 x plus a6 x up to an to the power of n. So similarly for 3-dimensional phi of x comma y comma z, a1 plus a2x plus a3y plus a4z plus a5x square plus a6 y square plus a7z square plus a8xy plus a9yz plus a10zx plus amz to the power of n. So here alpha 1, alpha 2, alpha to the power of alpha n or a1, a2 equal the coefficients of the polynomial. Also these are known as the generalized coordinates. So n is the degree of the polynomial and the number of polynomial coefficients n. So next, what is meant by simplex, complex and multiplex elements? So the finite elements can be classified into three categories. There is simplex elements, complex elements, multiplex elements, depending upon the geometry of the element and the order of the polynomial used in the interpolation function. So the simplex elements are those elements for which the approximating polynomial consists of linear terms. Thus, the polynomial is given by equations below represent the simplex functions for 1, 2 and 3-dimensional elements. For n is equal to 1, there is a linear model. For one-dimensional case, phi of x is equal to alpha 1 plus alpha 2x or a1 plus a2x. For two-dimensional case, phi of x comma y, alpha 1 plus alpha 2x plus alpha 2y or a1 plus a2x plus a2y. For three-dimensional case, phi of x comma y comma z, alpha 1 plus alpha 2x plus alpha 2y plus alpha 4z or a1 plus a2x plus a3y plus a4z. So the complex elements are those for which the approximating polynomial consists of the quadratic, cubic and the higher order terms according to that in addition to the constant and linear terms. So complex elements means for the approximating polynomial function which are consists of the higher order terms and the quadratic and cubic terms. For simplex and for simplex terms, the element will be of simple 1D elements which are linear. Okay, simplex and complex are of linear terms. Multiplex elements are of some higher order terms. And the complex elements may have a same shape as simplex elements, but will have additional boundary nodes and sometimes internal nodes. And the multiplex elements are those whose boundaries are parallel to the coordinate axis to achieve the inter-element continuity, and whose approximating polynomials contain the higher order terms. The rectangle elements is an example of the multiplex elements in two dimensions.